Hi everyone, Nas here from Info.Tech.Journal. Thank you for viewing. If you're watching this again, I thank you for coming to the channel again. If you're new, basically this channel is just a way for me to record technical journal entries that I find through either work that's interesting or throughout my studies or recertification. So in this particular video, we're gonna be working on OSPF. Okay. Specifically with OSPF, the ones we're gonna be focusing on is we're gonna do LSA link state database optimization, or just shrinking it down. When you have the graph, it's a little bit too big. It might cause problems with network convergence if you have a convergent event. And it's always nice to, like, if you have hedges or a tree, to trim the tree down a bit just to make it a bit more presentable, or in other words, with network, just to optimize it just a little bit here and there to ease your mind in terms of your network operations. Okay. For this one, what we're gonna do is we have OSPF. We're gonna have OSPF multiple areas, and then we're gonna use specifically the stub command. What the stub command does is it suppresses LSA type 4s and 5, LSA 4 and 5, which is basically your ASBR LSAs and your external LSA. From there, we're also gonna play around with the stub, but with the additional flag of no summary. No summary suppresses LSA types 3, as the name suggests. It's a summary LSA. All of this is done between areas. Okay, so we're gonna optimize that as well. As additionally, in this particular video, we're also trying to optimize LSA types 2, okay, which is your network LSA. Okay, your network LSA. So this is slightly done differently. This is not done with the stub or no summary. This is done basically with your network types, with your OSPF network types. To achieve this, we're gonna do a simple lab. The lab is basically, we're gonna have a few routers. Okay, we're gonna have one router here, one router here, one router here. Okay, I'm gonna say R1, R2, R3. Okay, R1, R2, R3. For this particular segment, let's just say this is gonna be in area 2. Okay, this is gonna be area 2. And then we're gonna have an R1, 2, 3, R4, and R5. And R4, R5 respectively, they're gonna be in area 0. Okay. Then we're gonna have another area here. Okay. Or I'm gonna just make some loopbacks. Okay, loopback. I don't want to get another router. But this loopback is gonna be in area 3. Okay. And then also there's gonna be a few loopbacks in we'll just redistribute this. I can't spell for some reason. Okay, a few loopbacks for us to redistribute in, because we want to generate some LSA type 5s, of course, because we're trying to suppress LSA type 5s. Okay, so from here, the primary purpose of this lab, this particular section, is just for us to see the additional type 4s and type 5s that will be generated by this router. This router is effectively now, since it has redistribution and another area, okay, this router is basically your ABR and your ASBR. So it's gonna pump in to area 0 those LSAs. In area 0, we only have a router R4 and connected to R1. R1, since it's just connected to another area, R1 is just our ABR. This particular area, okay, we can make it a stub, because this network is quite simple. As you can see here, there's no other way for any packets, Okay, any packets within this area. Oops, sorry. There's no other packets within this area to go out. There's only one direction flow. And when we look at the OSPF database later, there's a clear indicator on where we can decide to actually make an area a stub. Okay, so this area is going to be our stub area. Okay, that's our stub area. In terms of IP addressing, we're going to keep it simple. Everything for the primary OSPF components, we're just going to say 10.0 XY and Z /24. XY being the router, the smallest number first. So let's say if it's this link, is going to be 10.0.12.1 and .2. Similarly here, it's going to be 10.0.14.1 and .14.4 for that particular link. Similarly, also for area 3, for this one, we're just going to make some bogus numbers, maybe 2 or 3 interfaces, and we're just going to make those interfaces loopbacks and include them in area 3. For our loopbacks here, for our redistribution, we're just gonna make it 5. So we're just gonna say 5.5.5.5 and 5.5.5.5 and 5.5.5.5.5 all /32. We're just gonna have a few so we can actually see a significant size and the link state databases for each routers, just to make it semi-realistic. Of course, in a real environment, the link state database will depend on the actual size of the environment. So it might be bigger or smaller. Okay, without further ado, let's go to our GNS3 environment. If you're following along, you can just take a screenshot of this. It's not the best of drawings, but it's sufficient for a quick journal entry. Okay, let's go to GNS3. Okay, I have GNS3 open. We have 1, 2, 3, 4, 5 routers. 1, 2, and 3. Okay, and then a 4 and a 5. I'm gonna connect them together. 0, 0, 1, 1, 2, 2, and 0, 0. I'm gonna open the label. So we have the labels in, and we're gonna power them on. Scoot it a bit, zoom in a bit. Okay, hopefully it's visible. And let's start assigning the IP addresses. If you're pretty familiar with assigning IP addresses, which I'm pretty sure like most of you are, if you accidentally find my videos, you can probably skip forward. This is just me assigning the IP addresses. Nothing too fancy. Oops. 4 and a 5. So we have that. Let's move this a bit to the side and shrink this down a bit. Okay, yep. Okay, let's start with R1. R1, we have Ethernet 00, and I'm going to open my trusty tool, which is Notepad++. I'm going to say multi interface Ethernet 0, the address 10.0.121. That interface. And this is gonna be in, okay, I'm not gonna do that. I'm just gonna do the traditional way. Wait, let's just say router OSPF1 router ID 0.0.0.1. Okay, and I'm gonna so here, and I'm gonna say okay, this one is gonna be IP OSPF one area. That's gonna be in area 2. Okay, next one is interface internet 0/2 IP address. Okay, 10.0.14.1. Copy this. This is gonna be in area 0. No shut. If you're new and then you're thinking, oh, why is the router ID 0.0.0.1? The router ID is not an IP address. It's just a 32-bit number. So it is up to you to decide what the number is. Just make sure it's consistent. And if you do have a policy that you follow in your organization or your company, follow to that policy. Depending on your senior engineer or your network architect, they might have a preference in terms of your router ID. Okay, so we're pretty much done with 1. Let's see if the number works. Okay, 1's done. Let's go to router 2. Router 2, we have 0. Okay, so just change router ID. Let's go to 2 and copy this. Oh, I'm gonna copy this, sorry. Oops. Paste. This is gonna be 0.1. And this is gonna be 2 and 3. And 2. This is gonna be 2. Well, interesting. What in the world am I doing? Excuse me, let's fix this. Okay. I copy and pasted the wrong thing. Okay, correct. It's gonna be 3.2 in area 2 and interface is 1. And that's it. No. Okay. So we should see a neighborship follow coming up. Yep. Now we see OSPF has gone from loading to full, though we know that works. Let's go here. 3 0 1. Three. It's good. Let's go to 4. 4 is 0 2 and 0 0. 0 2 0 0 is gonna be 1 4.4 in area 0. And sorry, it's not 0, it should be 4 5. So this is actually 0 2. And this is 0 0. This is gonna be 4 5.4 in area 0. And then router ID is gonna be a 4. So we're gonna go here. Right, that's it. Now last one is 5. 5, again, we have a few things that we need to do. It's a lot of loopbacks. So I'm just gonna go here, delete. 5, area 0. And here is when we're gonna do a loopback. Interface, loopback 0, IP address. So 10.0. Let's say 33. Not 33, sorry, by 5.5. IP OSPF 1 area 3. Then interface loopback let's say 1.5, and copy this. So this is gonna be 5.5.5.5 slash 2. Again, if you're no, you can skip this. Two, copy, paste. 5, copy and paste. That should be enough. We said, yep, that should be enough. Or we can do another one. It might be a little bit too many already, but yeah, I'm just doing 1.5 long. Yep, okay, let's copy this. And we go to order 5. Yeah, let's go to our OSPF process. Router OSPF 1. Redistribute connected. Okay, we're not gonna worry about the other metrics and other components as well. We're just gonna say redistribute connected subnets. Okay, and that. And then let's go to router 3. It's the farthest edge router. So this is where we actually start our work. So if I say show IP route OSPF, we would see some OIAs, which is basically inter areas. And then we also see our E2s, which is our external types. So by default, it's E2. So we see all of this. And then this is where we're gonna start our work. So if I say show IP OSPF database, okay, you see this is for router, the router ID 0003, which is itself. You have your router LSA. Okay, this is router type 1, and this is your network LSAs. Okay, this is what we're gonna summarize or optimize later. So now you have your summary, which is your type 3s, your type 4s, and your type 5. If you notice that all of these, right, comes from a single source, your advertising router, which is 55555. And then if you look at 555, the way you read it, from 555, this is the router that has these particular external links. We have to go to the link of 555, which is reachable by 0.0.0.1, because the one who generates these type 3s, type 4s, and type 5 are going to be your ABR, particularly for this particular one, which is the ABR residing between the two areas of area 2 and area 0. Okay, you have to remember that. So that's why it goes like this. If I want to go to an external route 5555 for link ID, this is the router that I need to go to. Okay, this is the link ID for this. This is the router that I need to retrieve, and this is how I get there. Advertising router. Okay. If you say here show IP OSPF border routers, and then you can see that we have two entries here. One is, as I mentioned before, the ABR, which is 0.0.0.1, or our router 1, and we have 0.0.0.5, which is an ASPR. Okay, this has two functionalities, but it's just assigned here as an ASPR. Okay, if you want to see more details, we can just say details here. And then you can see here that 0.0.0.0, okay, has a cost of 40. And then this is via 23.2. Okay, because 23.2, because this is 23.2. This is how it learns it. Okay, the source is again from 0.0.1, because that is where the area learns it from. Okay, and then flags for pathless and partial SPF, we don't have to particularly worry about it as much. Just a quick note, if you're reading about this, it's something to do with how OSPF behaves. Within a single area, it is true that it is a linked state, okay, routing protocol. But the way it behaves when it does inter area, okay, versus intra area. Intra area, internal area, it's link state through and through. Inter area, it behaves like slightly like a distance vector because each area doesn't have full visibility of other areas. It is whatever the ABR or ASBR tells the other routers in that area of the view. So rather than it knowing the full map of the other area, it just says, I have a route to go to, let's for example, I have a route to go to 55555. How do I get to 55555? It doesn't know how to get to 55555, but it knows that it just needs to get to its ABR, and the ABR will then handle the rest. So it doesn't have full visibility. So in that sense, it is distance vector. Hopefully that's not a bit confusing. And when I'm watching this entry again in the future, hopefully I'll remember it again. Okay, let's continue. Now let's try to summarize this. When you're doing optimization, you have to remember that when you want to suppress or reduce your links and databases, particularly for this one, when we're using the stub flag for LSA type 4s and 5s, you have to remember that using a stub flag or adding a stub on an area is not a hitless change. What do I mean by it's not a hitless change? So let's go to router 3, then conf router OSPF 1, okay. Area, what is the area? Area 2, I'm going to say the stub. Okay. When I say area 2 stub, it will kill or you will lose your adjacency with the other routers, because remember, the stub flag for OSPF, okay, especially in the exchange between the neighbors, have to match. For this instance, it is no longer matching, so that's why it is not a hitless change. If you were to do this in a production network, make sure you have a maintenance window to do this, and of course all the other procedures like a change request and approval to do it as well. Okay, so if we go to now router 2, so basically I'm gonna say to never mind, I'm just going to here router OSPF 1. Okay, before I do that, let's just look at the database again. To show IP OSPF database. Okay, this is where I want you to pay particular attention. 1, 2, and 3, 4, and 5. When we say stub, it will suppress 4 and 5. So our link state databases will shrink, and this 4 and 5 will be replaced with something else. What is that something else? We'll see later. Okay. Area 2 stub. Okay. And then I'm gonna go to 1. So you see here, we've lost connectivity to 1. We've gained back to 3 because now the stub flags for 2 and 3 are a match for that particular area. So I'm going to say router OSPF 1, area 2, stub. Now down to full, it's going to flap, and now it's loading to full. Let's go back to where we saw on router 3. On router 3, when we looked at the initial databases, we did see 4 and 5. Let's say 4 and 5, okay, which is our ASBR summary and our external links. Now, if you like a show IP OSPF database, as you can see here, now we do not have 4 and 5. We do not have 4 and 5. What we do have now, if you notice now, is that we have a summary link, but then now we have a link to 0000 that originates from 0.000.1, which is our router 1. What does this particular entry mean? Okay, what does this particular entry mean? If you notice that initially we do not have that entry, it simply means if you just say show IP route, now we have an OIA, okay, but with a star, as you can, you already know that a star means candidate default, and this is basically just the default route, which is basically a default route. This still maintains the reachability for our area 2 to exit out of the network, out of its area to the ABR. But then with this particular entry, it suppresses 4 and 5. It suppresses 4 and 5. Okay. So for instance, we want to step this one step further. We want to suppress now or hide in this area, okay, the summary LSAs, basically the inter-area information. Because again, the same concept applies. If your particular design doesn't have two egress or ingress points for this particular area, and you want to minimize the links in database size, you can also do this. For this particular command, right, we don't have to apply it to all the routers because all the routers exchange with each other the stub flag. This is just an internal process that's done on the ABR to suppress further your LSA type 3, which is your summary LSAs. So the way we do this is, okay, just pay attention on router 3. We have all these OIAs, okay, the additional ones, and for our LSA type 3s, we have 4 particular entries. Okay? So we're going to go to R1. With Stub, we have the no summary. Okay, no external capabilities. We'll discuss it another video for this particular journal entry. But in my particular journal entry, this one, we're more interested in just having the no summary. If you notice previously when we added Stub, it will flap or it will kill the neighborships because the stub flag is not a match. But then when we say stub no summary, as you can see here, that we do not get the full to down message or any other messages, because this, once you change everything to stub, adding no summary is basically hitless. Okay, except for some minor LSA exchanges or updates being exchanged between the routers in that particular area. So let's go back to router 3, and if we say or issue the command show IP route, as you can see here, all the other OIAs are now not present. Reachability is still the same for this area because again, we only have one ingress and egress point for this area 2, which is an R1. So having the default route pointed to R1 still achieves the same effect. Again, maybe I'll do another video on consideration for traffic engineering, but then again, a separate journal entry. So now let's go show our database, show IP OSPF database, and you can see here now we've made the table that tad bit smaller. Okay, we've achieved our first objective, which is basically we want to suppress 4 and 5, LSA 4 and 5. Now we've minimized and suppressed LSA type 3 to the bare minimum. Now we're going to do something else with LSA type 2. If you notice that LSA type 2 is basically, if you were to say show IP OSPF, and let's just say, okay, database, and then I'm just gonna say summary. It's not actually summary. It's eluding me right now. It's not border routers. It's neighbors. Oh yeah, let's just go show IP OSPF neighbors. Okay, if you say show IP OSPF neighbors, okay, you have full and BDR. Okay, depending on the network types, if it's the network type, if I say show IP OSPF interface Ethernet 0/0. Oh, sorry, not 0/0. Which, okay, I'm on router 3, so it should be 0-1. If you notice that it has an election for DR and BDR. With DR and BDR, the network types is broadcast or non-broadcast. Okay, with that we would have to include LSA type 2 because it's a router LSA. It just shows you that there's DRs and BDRs in it. Okay, so let's say if I say show IP OSPF database router, let's just say router 0.0.0.0, right? Okay, now you see here, this is basically our router LSA, and then this is the information here. In OSPF router 003, we notice that we have 002 advertised. This is the router link. This is the link state age. You don't have to worry about that. Okay, designated router for this particular one is this IP address. So as you know that 23.3 is the designated router for this particular link, router ID, designated router for the other link, which is 1 and 2, which is 10.0.12.2. Then the interface is this. Basically, this is this information on when you have the elections for your DRs and BDRs. If you want to suppress the DR and BDR, for this particular instance, it's just a point-to-point link. It's not a broadcast link. Okay, it's just a point-to-point link. To suppress it is actually quite simple. So if you go to the particular interface here, interface Ethernet 0/1, you say IP OSPF network. You have these few options. For this particular one, we want it to be point-to-point. Okay, it's gonna be loading full. Okay, it's not good practice, but then to just have it on one side, but then we'll just see what effects it has on our database. So IP OSPF database. Okay, we still have network types too, but let's go to R2. It's on E1, so let's say interface Ethernet. Interface Ethernet 0/1 IP OSPF 1 area 2. Oops, wrong one. This is not what I want. And then OSPF network point-to-point. And we're gonna just go to interface Ethernet 0/2 0/0, and we're gonna issue the same command. We go back here, we're gonna say show IP OSPF database. As you can notice now, once they agree on the two interfaces being point-to-point, we have now suppressed one of the LSA type 2. Your router is to say, if you say now show IP OSPF neighbors, if you compare to the previous command we did, where is it? We have a status here of BDR for 0.0.0/2, meaning that R3 was the DR. But now we have it being a dash because there's no DR and BDR election. So if I say show IP OSPF interface E0/1, now the network type is point-to-point. If you want to make sure that this other entry, where is it? This other entry to disappear, we simply just go to R1, we say interface Ethernet 0/0 IP OSPF network type point-to-point. Okay. Now it flaps. If we go back to R3, we should not have any more entries in our database for area 2. Okay, let's just wait till it disappears. Now, once it converges, we only have our router link. We do not have any more, if you notice here, our link, which is LSA type 2, no more. We have type 1s, and then we have our summary. So this is how we can reduce the link state database and optimize it a little bit. Of course, in this video, it's not going to be as impactful, again, because in this particular video, we have a very small topology. It is not as big, and so the link state database is not as huge as well. So we see minimal changes. But then if you have a bigger upscale network, you would see the difference in the database. Just so you have a little bit of I would say a trim down tree. The graph is a lot smaller. So if you do have a convergence event, it doesn't have to have a lot of additional information just to regenerate the graph for that particular area. And it's slightly less work for your ABRs and ASPRs as well. So that's the particular video entry, journal entry for this one. Hopefully, if you did find this video, I hope you found it useful, helpful in a sense. And for me, this is again a journal entry for me in the future, so I have something to refer to for any future projects. If you do like this, maybe you can give it a thumbs up, subscribe to future videos because I'll be making more video journal entries as well. Thank you for viewing, and I hope you have a good day.